I run that now. In the meantime, I think it's high time that you start preparing for the term and exams. And pattern for the term and exams, I'm sure that you know that several exams will come. Yeah. Please ensure that you bring your calculators for the term and exams, because some of the problems which we have done, the finding out the impurities, kind of things, might be asked some of the questions. Carry a calculator with you. In terms of your preparation for the term and exams, I believe that if you have been contents, if you have followed the live classes that we have done, we have gone through the should not be a difficulty for you, not be a problem when the industry is not yet with. I'm surprised. I'm quite surprised. We'll do one thing. So in the break time, we will take the first break. Please just mind this thing once. What I'll do is I'll just drop a email. NM, because again I talked to NM people. Yeah. They're called by this. Right? Please remind me once when we are taking the break. Just one or two people more and we can get started. By saying the voice is breaking, is the voice breaking for everyone? The voice breaking for everyone?
It is clear to me.
Okay. I think Amritangshu also is saying that the voice is breaking. Namrata, it is clear at your end, right?
Yes, Professor, it is clear to me.
Because I think several people they are saying, Deepthi is also saying that the voice is.
I'm not sure why it is happening.
Just check. For everyone, the voice is breaking. That's so. For everyone, is the voice breaking? For the other people also, is the voice breaking? Okay, fine. I'll try to be more closer to this particular mic, which is there, right? But yeah, share with me if you're having issues. Okay, so today, what we are going to start off with the ensemble techniques. This particular part not much represented in most of the learning materials which is there. So put that in the NM and upgrade material, the ensemble techniques there. But as such, if you open up a standard textbooks for machine learning, this particular part is not something which really gets much attention. Why? Because of ensemble techniques part, here we are not actually applying any new algorithms. But what we are doing is we are in some way or the other and matching algorithms, mixing and matching data sets so that you can get a better learner. That's what happens in ensemble. And I'll tell you why ensemble techniques have gained much popularity. What happened was competitions like Kaggle, right? In this kind of a competitions, your final benchmark, in most of the cases, how accurate the model is. Unfortunately, sometimes what also happens, I think we're discussing in the last session, the difference between the data scientist method and the difference with the statistician's method. The statistician always concerned about how this model is coming into play. When is this model working? When is this model not working? What is the effect of each and every variable on this particular model? The matter of the fact how each and every data, like if you include some data, how the model is behaving, exclude some data, how the model is behaving. All these are some of the things the statistician is very much interested in knowing. But come to the part of the data scientist. A data scientist is typically more concerned with how good results the model is giving. Not necessarily how the model is working internally, what is happening, probably is not much botheration of the data scientist. Now, in a bid to do this particular thing, right? So when the more concern is about how underlying what how the results are coming in, what happens is people doesn't take a hint as to how they are getting the results. So if you see these Kaggle competitions, I think Kaggle started somewhere around 2010. Before Kaggle, what happened was there was this Netflix competition there. And this Netflix competition, their proposition was very simple. Whoever comes up with any model, any recommendation model, which is at least 10% better than our existing model, we will give them $1 million. And that, by the way, is a lot of money. We are talking of this particular Netflix competition was launched, I think, around 2006. $1 million just for an algorithm, lot of money. People have not seen this kind of things in the market out there, right? A lot of people were working models, different kind of models came into, but none of the models were able to really get past parameter 10%, at least 10% more efficient compared to the model. Then what happened was a team, the top two teams were competing at that point in time. What they did was they collaborated. So they said that rather than competing, let's collaborate. Prize money is there. We'll probably share the bounty among us if you're able to do that. Then Bell Labs and I think two other teams, I think one other team, they collaborated and by a whisker, I think 10.03 was the accuracy of their model, like the increase in accuracy of their model vis-a-vis the Netflix algorithm, and that's how they won the competition. So this was the first start of that ensemble thing, an official start. Because previously to it, people were using algorithms in isolation. When they found that, okay, if my final endpoint is some particular object is there, object function, some particular accuracy is there, no matter how the accuracy comes in, as long as I'm able to reach the accuracy consistently, I should be good. What in ensemble model does is that models of the same kind of type, models of different type, models different proportions of partitions of the data, all that are being used, right? That is the basic premise of this ensemble techniques, right? So no new algorithm we are talking about. We are just talking about ways in which the models will be combined, right? Okay, let's move ahead. How the ensemble learning works. I think this is something which I had showed earlier also. So here are these three models which are there, right? This is the one model. This is the M2 model, and the third one is the M3 model. And this is typically a classification problem that we are trying to solve, right? And the objective of this classification problem is to separate out the pluses from the minuses. Very simple. Now let's say if we are taking the M1 model. The M1 model is built to separate out the pluses from the minuses. If I talk about the M1 model, what is happening is that while the model has correctly classified this red color, yeah, while these all the model has correctly classified. But because it's a simple model, the bias part, as you see, is quite high in the model, and these points are misclassified. The model classifies all these points as pluses, right? Anything over this line is plus, anything below this line is minus. That's what the model does. But see, all these points have been classified by M1. Misclassified. Once that is done, okay, let's look at some other model. So M1 model clearly is having a high bias. We are not able to get a good result from M1 model. Let's look into other model which is M2. Once M2 has run, once again you see that all these parts has correctly identified. In fact, in the M2 model, this portion of the negatives is the good thing which is the model is doing. But coming to on the left hand side, there are several of these points. So this time, these other points are also getting included. All these points are this time classified. The pluses have been classified, but along with that, a lot of classification also has, right? Class. In this particular case, if I draw the confusion matrix, the confusion matrix, what kind of a errors are we finding? I via M1 or via M2. What kind of an error I am looking at when I'm using M1 or M2 in a confusion? Yeah, anyone? Confusion matrix. I hope you already remember. If you see, what is happening is that all the negatives are being correctly classified, right? So correctly classified in the sense that the negatives, at least some of the negatives, see some of the positives are not being booked as negative. Right? That's the part. That's the good part. The positives are not being booked as negatives. If you see the case of the true negatives, right? True negatives, I mean, the case of the M1 model. The M1 model, if I see all these positives, okay, so these are the positive, but these are the false positives which we have got. These are the false positives which we have got. Has been predicted as positive by the model. These are false. Right? True positives are fine. True negatives, yes, all these they are negatives. False positive, fortunately, we don't have false positives. So in terms of the false positives, no false positives for the model, but yeah, in terms, sorry, no false, yeah, but there are, sorry, no false negatives from the model, right? But a lot of false positives are there. All these are the false positives which we have got from the model. Two negatives are there, that part is fine. Positives, this part only restricted zone. So false positives we have, false negative, unfortunately, we don't have any false, right? So that is happening with all the models, M1, that's happening with M2 also, and that is happening with M3 as well. So people say M2 is having false positive. Yeah, so all these models, M1, M2, right? Even I think M3. M3 is also having a lot of false positives, right? For the M3 part, all these points out here, here, all these points are the false positives which are there. False negatives are not there. Lot of false positives are there. So however hard you might have tried, you are not able to eliminate the false positives in spite of using many of this. Only thing that you can that comes to your mind right now is that okay, so plot the data like we have done right now. The plotting, what we find is that the different points which are there, false positives which are there, are at the different sides of the decision boundary created by this model. Now, if you combine the model, what is happening is that the voting of the combination of the model. So if you see the middle red part, all the models, all the ones M2 and M3, we are confirming that middle part we are having out here. That's the positive part. But then what is happening is that, right, the models. To understand this diagram well, almost 70% of the class already have understood. Okay, so see one part. In M1, the points which are on the top, these points are the false positive there. M1 is say M1 is finding detecting these points as positive, so they are not positive, right? Come to the M2, right? So M2, what has happened is all these points M2 has rejected. See M2, all the points are over this are what the as negative. So already there is some kind of a clash between what one is saying and M2 is saying in terms of some of these points. M2 is saying no. These are not positives, these are negatives, right? Come to M3, right? So M3 once again is also saying that I support M2. All these points which are there are not positive, right? They are probably negative. What is happening is that M1 by its own was unable to filter out these false positives. With the help of M2 and M3, by the way, it was clearly able to filter out some of these points, right? Okay, coming right M1 and M3. Let's look at M3 now, right? So for M3, what has happened is that these points for M3, all these points are fine, but are some of the points which M3 is saying that these are positive. That's what M3 is, right? The verdict as per also these points. Now you go to M2. Let's say what M2 is. So for M2, so what you had clearly done is that M2 had pulled out points, right? All these points already bring out, but unfortunately for M2 also, points M2. Now then take the help of M1. M1, what M1 is saying is that all these points are probably wrong. This particular part, when you take M2, we are correctly able to classify this particular part of the When you take one's help, you are correctly able to classify. Right? The task was not possible by models individually. That has been made possible by using a combination of the model, and that's what the underlying principle of this technique. Let me give an illustration, right? And I hope that everyone, even if you don't understand too much mathematics, be able to understand this. Let's say this is the buffet where you have been. Now in this buffet, as you see that, sorry, there are multiple counters. The objective of the restaurant owner is to ensure that the wastage in the restaurant is as low as possible. I'm repeat, the wastage is as low as possible. What will happen is that restaurant owner, what this head chef will ask several people come and taste the food, vote for that food. Right? This fine gentleman comes in, likes the food, and the chef takes a note of the portions that this person has taken. Then this fine lady comes in, right? She also binges a lot of the food. Already you can see that this and this food is the same both the places, right? She also binges on some of the food. So the chef takes that also into account, that what portion the lady has taken. And the final lady comes in. Once again, you see that here the same fruit is appearing here as well, along with some other fruits which I think the other lady also had taken, right? So once again, this portion 3. So portion 1, portion 3 is also taken into account. And finally, portion 4. At the end of the day, this head chef had to take a decision as to how much of each of the items make. So looking into the portions of well, what they are consuming, which is the item which is being more taken into account. Which is, I'm sorry, which are the items which are not that much in demand. Based on that, get entire assortment for the, and that's how your buffet part comes. Right? Next time when you go some buffet like this absolute barbecues or even some other specialties, find that intentionally they will probably give you a lot of starters, and the portion which is there, the main course. Generally, you'll find that, I mean, if you look at consciously, find that people takes very little portion of the main courses, because the starters, the kebabs, they take most of their plate or their stomach gets filled by them. Right? So again, that's rather application of the ensemble technique which is out there. How we can apply that. Now coming to why we are using this ensemble. As I've already showed you that one of the reasons of using the ensemble is that you are able to identify some of the lacuna which a model individually by its own was not able to. Right? Other thing is there that ensemble model by itself, ensemble model by itself, we are using ensemble models, it has been found that variance of the models, we need models with low bias and low bias. Ensemble, the variance of the ensemble models generally been found to be lower compared to the right. So just go to a mathematical model. Yeah. Remember binomial theorem that has been taught to you. So let's say that we have several models, say M1, M2, M3, 4, 5. 5 different models are there. 5 different models are there. Now, what we are going to do that you have found that on an average, the accuracy of these models are 80%, and the error that they make is 20%. Now, when you are putting all this model combination, that's what the ensemble model does, right? So 5 different models are there. Now, your prediction only go wrong if we are using something like, let's say that we have said that will take by the majority of the model. So your prediction will only go wrong when at least 3 of these models, they are making the wrong prediction. I think some comment from someone. Puna has some question. Classification, averaging. So Puna, I'll ask your, I'll respond to your answers when we come to that particular part. I think Pradeep is having a audio problem again. Once again, the audio problem happening for everyone. The audio problem happening for everyone. Pinkish is also saying that she is having audio problem. I think a lot of you are saying that there is some audio problem. Shubhendu is saying it's clear. Sound is breaking. Not very sure what's happening. I can do one thing. Okay, so some people are saying possible to keep the video off. Yeah. So what I'll do is, that's a good suggestion. I'll just turn off the video. Right? I'll just see how it is going. If that still doesn't solve the problem, maybe what we will do is we will I'll just log off and rejoin. That's what I'll do. So, okay. Let me just stop the video. Please let me know if you're facing the issue, right? Okay, so we were talking of this 5 models we have: M1, M2, M3, M4, M5, and the probability of success of the model is 80%. Probability of failure of the model is 20%. Because 20% times the model is making some kind of an error. Okay? So which means that if I'm taking a majority voting from the model, majority voting. So majority voting means that if out of this 5 models which I'm having, 3 of them, they are giving the correct answer, right? So in this particular case, I'm talking about a classification kind of problem. If of these 5 models which are there, at least 3 are giving me the correct answer, then I should be able to get the correct answer. So let's say that M1, M2, and M3 is saying that model belongs to class A, and M4 and M5, they are saying it belongs to class B. Just because of the fact I am going to take a majority voting, and since the majority of the people are saying it is class A, I'll take class A. So which means what? That in order for this model to give me incorrect response, at least 3 or more of them give me a wrong answer. Now, how that can happen, right? See, at least 3 or more will give me wrong answers. So, one case is there where 3 of them are giving the wrong answers, or 4 of them, they are giving wrong answers, or all the 5 are giving the wrong answer. So only in those cases, the model, the entire ensemble model will give you a wrong answer. But the matter of the fact is that, as you can see from the figures, from the numbers which I've written, the probability of that will be very, very less compared to the part where we are taking the probability of the model being correct answer. That's why when you are combining many of these models, answer generally get the validity of the answer, or the probability of getting the correct answer is much more compared to the case where you're using individual. The voice clear now, by the way, or still it is breaking? The voice clear now, or still it is breaking? The voice clear, or still it is breaking? Puna is saying way better, but Deepti and Amritanshu is still breaking. Better. Okay, so times happening. What I'll do, as I said, that let's continue for some more time, and then let's take a break, and I'll try to see if this can be fixed. At okay, let's move ahead. Many people are saying it's not so. One thing, Dr. Namrata, are you still facing the issues?
Professor, it is clear to me for some reason.
Okay. Because I think many of them, they are saying that it is not very clear. Many of them.
Are you using any headset or anything?
No. So I was using headset. Okay, let me just open up this headset. So I have removed the headset as well. Still it is breaking. Pinkesh, Anu, Pradeep. Is it still breaking? Pinkesh, Anu, Pradeep, the last 3 people gave the responses. Is it still breaking? Pradeep is saying now it is better. Okay. Anu, Pinkesh. Anu is saying better. Pinkesh is saying not better. Not very sure. Not very sure. Namrata, at your end it is fine, right?
From my end, it is clear.
Okay. Fine. So again, let's continue. We'll see. Thank you, Namrata.
Yes, sir.
Okay. So coming back was what I was talking about. That for 5 different classifiers make a problem to give a wrong prediction. Considering that there is a 80% success and a 20% error. Error of the ensemble classifier, right? It's only 0.05. That's the error of the ensemble classifier. And if you see out here, chance of all the 5 classifiers will make an error is 0.00032. While individually you have seen that individually each of them making error is 20%. But the probability that all 5 of them make an error, it's so very minuscule. And the error rate for the ensemble overall is 0.05, which is way lower than the probability of the individual models, right? So particular is important for interviews. So many a time in the interviews, they might ask this question. One is that you can always explain that how, in your own words, how a model can probably perform better when it's not ensemble vis-a-vis when individually the model is being used. Other is that if you can show mathematically, there will be no further questions, at least on this particular part. Right? Okay, let's move ahead. Coming to ensembles, there are many different ways in which you can create ensemble models. So I'll take the very simple one. So you can create ensemble model based on how you compile the results from these different models. Right? You can compile the results from the model based on averaging from them, or maybe take a vote from them. So averaging typically you use for a regression problem, and voting you can take for a classification problem. That is on the part of the result compilation. Also based on how the sample is being selected, you can create different ensemble models. In fact, the interesting thing is that the same model, right? So let's say that you have taken a very basic model. Let's say for the matter of the sake, you have taken a decision tree model. And in the decision tree model, what you have done is that you have used different partitions of the data to create different decision trees. So let's say you had features, 5 features which were there. Let's say that F1, F2, F3, F4, F5 features. 5 features were there. What you might have done that you might have taken for decision tree 1, you might have taken these 3 features, F1, F2, and F3. For decision tree 2, you might have taken F2, F3, and F4. For decision tree 3, you might have taken F3, F4, and F5. So what will happen in an effect is that because you are exposing the model different parts of the data, some features are not represented in some of these samples. Different kinds of decision trees. Right? So in just how you are using the data to give rise to different models which are there. Right? That was only based on the feature which is there. Now let's say that I had written all the features. Right? F1, F2, F3, F4, F5, all the features I've written the target. But example 1, example 2, example 3, example 4, example 5, these different examples are there. I have exposed my model only to example 1 and example 2. Some other 3 I have exposed it to only example 2 and example 4. Some other I have exposed it to example 2 and example 3. Because different sections of the data getting exposed to the model that we are getting, at the end, different trees will get created. Right? Anyone who didn't follow this particular point, anyone who did not understand this particular point, repeat. I'm open to repeating, but yeah, anyone who did not understand this particular aspect. One is that I can take the different features, goes in as input to my model, or I can use different examples. Okay, Amritanshu is saying repeat. Sure, Amritanshu, I'll do that. By the way, other people, Joginder, Pikesh, Ashutosh, I hope the audio is right now clear. I'm just hoping the audio is clear now. Okay. So what we said is that I think on the feature part, you understood that. On the examples part, I'm creating a decision tree. My decision tree 1 is created with example 1, example 2, and example 3 of the data. Decision tree 2 is created based on example 2, example 4, example 6. Decision tree 3 is created on example 1, example 4, example 7. So like this, I have exposed different portions of the data to the model. Same model I'm running. I'm running the same decision tree model, but I'm exposing different subsection of the data to the decision. That way, what is happening is that the model has remained the same, but because different partitions of data has got the model, the behavior of the decision tree itself, how the decision tree has been built, the different features which are there in the decision tree, that might change. Right? That is one way of creating a decision model based on different partitions of the data. Along with that, you can also use different partitions of the feature. Right? So different partitions of the feature, what you are doing is you are taking F1, F2, and F3 in one of the partitions. In other partition, you are using F2, F3, and F4. Right? So right there, like that, different columns of the data are exposing that. So net, different models, once again, though it's the same model which you have created, but again, how the model will be trained and how it will behave will be totally different from each other. Right? And the third one is a combination of the, so where you are taking a subset of the data and a subset of the feature. So taking different subsets of the data and the subset of the feature, you are creating this. Different subset of the data, different subset of the features, you are creating this model. And like previously, as I said, that different model, though it's the same model that you're using, but because different partitions of the data, different features are being different model. That is what how based on the sample selection you can one model set. Some question Jinder was saying by examples you mean the different sets of samples. Yeah. So again, each row of data is one example. Each row of data is one example. Now, if you combine a few examples, right? Don't expose the decision tree, or again some other model, let's say a logistic regression or a KNN model, the same partition of data, then it will create different models. Right? Okay. That was with sample selection part. And then there's also something based on the model that you're using. Sometimes you might use the same kind of model. I have continued using the decision tree, right? So that is the example of a homogeneous kind of ensemble. Though I have used an ensemble technique, but underlying model ensemble is the same. So that's the case of a homogeneous ensemble. Vis-a-vis, as you can understand, that the underlying model which is there, those are different, right? So on the data set, I have used a combination of decision tree, logistic regression, support vector machine, neural network, right? Logistic regression, all those things I've used, right? That's an example of the heterogeneous ensemble, right? So these are some of the things that we are going to discuss going ahead. Okay. But now my video is also on. My video is also on and audio is also on. I hope people are not facing issues. Puna has some question. Homogeneous ensemble has some model parameters also. Hey, Puna, we will discuss it when we come to that particular part. Let's talk about the averaging of the model, the averaging method. Amritangshu is saying voice breaking still. Again, Amritangshu has some issues happening for the others as well. Is it happening for the others as well? Is it happening for the others as well? In middle, it is breaking sometime. I'm not really sure. I don't remember with your batch or some other batch we were having some issues. But in the middle, it is breaking sometimes. See again, whenever it is breaking, please just put it on the chat. I'll try to repeat that particular part. Unfortunately, I don't have any control over it. But at my end, the network shows very stable network. But yeah, there might be some glitches at some point. Yeah, please let me know. I'll try to keep up with that. Okay. First, coming to the part of averaging. Right? Let's come back to our chef once again. So in the simple averaging case, what the chef is doing is that, okay, simple averaging comes to effect when you're using some kind of a regression model. Three models are there: model 1, model 2, and model 3. Just a simple arithmetic average or mean of the model is put as the output. Right? So for a regression model, what you're doing is the average of the three models which are there. The simple average of the three models, you're putting it as the output of the output. That's the simple averaging. Right? Now, come to something which is the different or complicated, which is the weighted average. So as you can very well understand that unlike the simple averaging, the weighted averaging case, there is some kind of a weightages being on the model. Now, how you can give different weightages to the model? Very simple. Very simple. Right? You can give weightages based on accuracy of the model. Right? That is something that you can do. You can give the weightage based on the proportion of the data which has gone into the model, proportion of data. So you might ask that how the proportion of the data. See, in the case where we are not exposing the model to the same subset of data, right? So some model has been exposed to more subset of the data compared to some other models which are exposed to the lesser subset of the data. That can also be used, right? Something like you have the R-square value which you have from regression. Say if you're using a simple regression, and you're creating a ensemble of regression models. What you can do is based on the R-square value that you have got, so that R-square value can probably act as the weight of the model. Right? Like this, there are many different ways in which you can go weighting. But at the end of the day, once you fix the weightage of the model, what you do is that whatever is the prediction coming out from the model multiplied by the corresponding weightage, and that gives the final model. Right? In this particular case, the weightage adds up to 1. What you can simply do is the summation wi that you can do. Weightage into the predictions: 0.4 into 45 plus 0.3 into 40 plus 0.3 into 60. Right? Sum of that will give you the weighted prediction from this. There can be some cases where the weights are not the same. Let's say that this is 0.7, this is 0.8, 0.9, maybe R-square values. Then what you simply do is once again the summation of WIPI divided by the summation WI. That is what you are going to do. The previous case, because 0.4 plus 0.3 plus 0.3, it adds up to 1. So the dividing by that summation WI was not required. But in the case where you are using some other metric which is giving you defined weight values for your model, the same formula, summation WIPI, but divided by summation WI. That will give you the weighted average of the model. Okay, so Pinkish is asking when weight is more than 1, then we need to divide. Not necessarily. If you have weight less than 1, then also you can do, right? Let's say, for example, so that is not a very common case that where you are having the weight less than 1. So let's say this is 0.1, 0.3, 0.4. This particular case also, you see the weightages. The weightage is only 0.7. Here, once again, summation WIPI by summation WI, right? But again, this is a more generic formula. Forget whether the weight is more than 1, less than 1, equal to 1. Irrespective, all the cases you can apply the model, right? The weighted average model. Come to next, called the voting. And by the way, voting is applicable for classification model. We've already discussed this. What you simply do is you take a majority voting, right? So whichever class is coming out as majority, just take that, right? So in that way, has some semblance with regard to our KNN model which we have done, right? K nearest neighbor also has the same kind of a interpretation. Whatever is coming out as the maximum, as the mode representation, that for a vote. Again, this is the called the hard voting. Particular example which we showed you, that was the case of a hard voting, right? So what it does is it uses a simple mode technique. Whichever is coming the maximum number of times, that is being used as the representative class. One way it is fine, but a problem is that it does not take into account underlying model trait. See, typically, whenever we are talking of this classification kind of models, most of these classification models, most of them, not all, can be converted to some kind of a probabilistic model, right? And how we get the classification is already studied logistic regression. Whenever the value of this particular probability is more than a particular threshold, we put it class A vis-a-vis some other class of C, right? When we are using the simple mode technique, what we are just looking at is the output of the model. We are not taking underlying model traits into account. For example, see, this hard vote is almost similar to how election happens in our country. In election, you have several of these different seats which are there spread across the country. I think some 300, some 200 something seats are there across the country. And what happens is that you look the hard vote to each of these, right? Each of the seats pockets based on the hard voting determine that who was the majority and give the seat to that particular party. Overall, when the votes are being counted based on the majority of the party getting who are giving out the verdict. But sometimes it might so happen that maybe the winning party has got some, let's say, some 44% seat, and the next party which was behind it, it just got 42% seat. Right? If you look into the underlying mechanism, one got 44%, one got 42%. So if I talk about the underlying voting traits, might argue that no, there is not a majority, but again, we have taken a hard voting, that particular aspect is ruled out. There is hard voting, soft voting, which is there for this class probability problems, right? So what we do, rather than taking the hard voting, we take into account the probability returned by a particular model. Let's say you have three models. One, you're going to take a majority voting. Let's say that M1 is saying that this 0.7 probability of A and 0.3 B. M2 is saying that okay, 0.9 B and 0.1 A. M3 is saying 0.6 A and 0.4 B. If I take a hard voting, as you can see that M1 and M3, they are saying the majority class should be A, while if saying no, it should be B. But again, if you take a soft voting, just take into account what is the total probability which has come in for M1. So for A, for class A, the total probability which has come out is 7 plus 6, that is 13 plus 0.14, 14. So 1.4. 1.4 is what you have got for A. But if you look for B, so B here, right now we have 0.9, then 0.3, which is 0.9, and then 0.3, that is 1.2, 1.2 plus 0.4, 1.6, what we have for voting. So the hard voting, it A, if you're taking of voting. That's also another way in which you can arrive at the majority classes for this. Now, some of you might ask that, Professor, is there any rule of thumb as to when to use hard voting, when to use soft voting? There is actually no rule of thumb. Depending on your business scenario, depending on which one is more important in a particular case, you need to figure out that whether you are going to resort to a hard voting or again you are going to resort to a, right? Okay, let's go ahead. Now, creating ensemble. See, at the end of the day, what you do is need diversity. Whenever you are creating an ensemble model, the thing which is paramount in the ensemble model, basic principle is diversity. So how can you get diverse model? One, you can use different models itself. That itself will bring out about diversity. The model itself which you are using, those are different. Other thing which can be is that population which you are using. So for same model, you are using different parts of the data. The population which you're exposing the model to, that is different. Right? Difference in the hypothesis which has been used, right? The underlying hypothesis that you are trying to test, that is different. Right? Again, this will take look into some advanced techniques. I'm not going into the difference in hypothesis part. The difference in techniques we have already talked about, the difference in models, and the difference in initial seed. See, Python, you can actually give an initial seed, which the model gets partitioned. Same model, multiple different seeds, it will multiple different models. Right? Let's more in details. Remember bias variance part that we have done. Typically, all the models that are being used in the case of ensemble model, they are generally having a high bias. Right? Now you might ask that, Professor, if they are generally having a high bias, then how does the model building happens? Very simple, right? Earlier you are using one model. This model is having high bias. Data coming out here. Here you are using multiple models. So this is the coming from M1. M2 is also a high bias model. But this is where values are centered. M3. What is happening in M3 and M4? This is what happening in. So see the data. Different models, all of these models, they are very simple models. By the way, see, you get a high bias model only in the case where the underlying assumption about the model is very simple. Right? If you remember, we had done this in the last session. Underlying assumption, it creates a very simple assumption of the model. But again, combine multiple models, which by the way, make the same simplistic assumption, but again, for different features of the data. So at the end, again, though you'll be having models with high biases, if you combine those high bias model, once you combine those high bias models, see this particular model which I'm having, which I've drawn on the screen right now, it doesn't have a high bias anymore. Right? Bias in this particular model is pretty low because the combination of this, all this will get good fast this particular zone. Right? Got the idea? I hope so. The ensemble part, one thing which we can do, high bias part, taking care of in this way. Similarly, the variance of the model. Okay. There's the case, the model with a very high variance. Generally, what is being done is that typically when you are using the ensemble models, probably try to filter out the parts models which are probably giving which are having a high variability or even bias is probably more than a particular threshold which is there. So you restrict your model to a certain domain, and in that way you can also check the amount of variance which should be there in the model. Ahead, get this, open up a whiteboard. Have this scenario where confusion matrix 1, this confusion matrix 2, right? Confusion matrix 1 is for model 1, M1. Confusion matrix is for model, right? Well, one is predicted. First, look into the model and find out that the performance of M1 in finding out the true positive vector, or it's the M2. Like I'm just saying M1 and M2, you can generalize it to multiple models. Each of these models is giving you a high proportion of true positives. Which of them are giving you a high proportion of negatives, right? So maybe your model which is giving you a high proportion of true positives on the true negative front is probably failing a lot. The other model which is probably giving you a very good result for the true negatives case on the true positives, probably giving a very bad result, right? So what you can do is whenever you are combining the model, can take this particular thing also into account. That in this particular model, I know that if I need to reduce the amount of false positives which are there, maybe I should not use M1. I should rather go at M2, right? Or I should give more weightage to what is coming from M2 if overall I need to reduce the false positive model, right? So those are some of the ways in which you can tweak the ensemble model so that it works as per your desired needs, or right? That way you can bias part we have already talked about. The variance part is also something that you can use from this ensemble models, right? Okay, now let's come to homogeneous ensemble. As I've said, most common type of ensemble, the same base learner, and though the model is homogeneous, but data sampled into different subsets. So subsets can come based on different examples. Subset can come for different features will give different subsets, different examples, different homogeneous ensemble, right? Most common kind of ensemble, right? Now bootstrapping method, what happens that you create samples of identical size from a given data, identical, right? But the way in which sample how one that you can use probably sampling with replacement. The other case is that you are using sampling without replacement. So as you can understand that if you're using sampling with replacement, that is sampling without replacement. The without replacement case, what will happen is that the bootstrap samples, what you get, are very distinct of each other, and a subset of data which has been given to one sample will not come into the other sample. But if you are taking sampling with replacement, then what is happening is that data points might come into many different samples of the data. When you are exposing this particular model, exposing this particular bootstrap samples, different models, what is happening is that multiple parts of the data are getting exposed to the different models. So overall, the accuracy of the model leads to this, right? Example. Here, what we are doing, remember our key-fold cross-validation. The key-fold cross-validation, though that's a cross-validation technique, but when you are creating the different folds and these models are running on the folds, so in some way or the other, it is nothing but some kind of an ensemble, isn't it? Because what is happening is that at each and every runs, this particular model is being exposed to different partitions of the data, right? Because this one data is left for validation, all the other parts are left for queries. So at different runs of the data, it is getting exposed to different subsets of the data. And these subsets, as you can understand, if sampling with replacement, the same kinds of subset that you'll be getting, right? So that's how, if your key-fold cross-validation works, then your scrapping that will also work. So here, one of the popular methods is the bagging method, which combines the result from multiple models, as you understand, to get a generalized model and create the different subsets. The scrapping method. Data with replacement is what has been taken. And again, one difference with the k-fold cross-validation method that we have talked about, subset maybe of same size or sometimes also less than that. That's it. That's the part that's different from what k-fold cross-validation. It's the same size of the original data set. Obviously, it is not the same as in k-fold cross-validation. When the size is much lesser than the original data set, probably the method merges with the k-fold cross-validation. My question to the class that if I am taking subsets of data which are of the same size as the original data set, then how am I exposing the model different partitions of the data? If I am taking subset of data of the same size as the original data, how again are exposing the data to multiple? Okay, wonderful. Puna has an answer. She's saying that the Anu has given the other part. Wonderful. See that we have data set. 10 different rows of data are there. And from these 10 different rows of data, if I would like to create different subsets which are of size 10, once again, saying voice is breaking again. Is the voice breaking for everyone? Is the voice breaking for everyone? I think 2 or 3 voice break. Let's do one thing. After this, we'll take a break. We'll take a break, right? Just give me 1 or 2 more slides. We'll take a break, and then I'll try to restart the system and see whether this particular problem gets mitigated or not. the data selection part with tagging. Okay. Some of the people they asked what was the question. The question was that the last point. Subsets may be of same size or less than that of the original data. It can of the same size of the original data or even less than the original data. Now, if the subset is the same size as the original data, then how will create different models from the data? So I think of the people they answered one that you can take a subset of the feature, not the subset of the data, but a subset of the feature that will create different model. The other thing to do is that we can probably take a sampling with replacement. That particular case, in data might be exposed to some different conditions. Here is the example. There are some 12 rows of data which are there. And from these 12 rows of data, what I am doing is I am creating sample of size 5. And I am doing that as a sampling with replacement. As you can see in the first case, 1, 10, 3, 8, 3 comes in. In the second case, 4, 11, 9, 3 comes in. So this 3 was getting repeated out here. Go via this. 1 was repeated here, 1 is coming here, right? 5 is coming twice in data, right? 6 was not there. So yeah, like this, we can get different samples of the data. Now, once you have these bootstrap samples, here we have created bootstrap samples of size 5. Sorry, you can create samples of size 12 as well, right? But again, because you are sampling with replacement, chances of that not get many identical samples, and that's the way you get different subsets of the data. And when you expose that, the main model get an ensemble model, right? These are the statistical properties. One is the IID part, drawn from independent and identically distributed data set. And then the representative part. So when you split a subset of the data, you should split subset of sufficiently larger size that complexity of the underlying distribution can be, right? Okay. And the third one is the bootstrap samples as much as dependent as possible. Here actually you can do a test of a proportion which is there. Very hypothesis testing. A test of proportion is something that we can do. If we see that the proportions of the data are too much matching, the features and everything with something that you have already seen, maybe you can discard this and different sample. But again, all these things adds a lot of computational complexity and process. Right? Okay. Let's do one thing. Let's take a 10 minutes break now, right? 14 my clock. Let's come back exactly at 8:54 time. Let me just start my system and see if we can get this problem. I was asking the previous slide. Okay. The last slide that we had, right? Drawn from independent identically distributed data set, representative and part imported from the IIT. Right? Okay, so let's take break and let's come back exactly at 8:54. So Namrata, you are there?
Yes, Professor.
Namrata, what I'll do is I'll just for once I'll just restart my system, check the network connectivity and everything. I hope the problem should not be there, but yeah, some of the people they're having these issues. Let me rerun this and come back in 10 minutes. Fine?
Okay, sure.
Okay, thank you so much.
No problem. Meanwhile, requesting all students to give your feedback about the session over the link that is provided in the chat box. Thanks.
Sorry, it took some little time to get the system back. I hope now the voice and the video is fine.
Hi, Professor. Yes, to me it is fine.
The others, participants, I hope it is okay now. The system reboot and everything, it took a little time. Sorry for that. Not to worry, I'll make it up. Good, good. Thanks everyone. Let's come back to the session. Let's come back to the session. The last part, what we are doing is the part. We were talking of this ensemble and how by simply using different partitions of the data, we were arriving at trapped samples from the same sample of data by using the different features which are there. By using a different subset, you can arrive at different ensemble models which are there. So those were some of the things that we discussed. Okay, coming by the just a moment. It's taking a little time for that PPT to come up, but yeah, time it. Yeah, Purna, I'll share my screen. How it's not coming up. Just a moment. Okay. Trying to share my screen. Just let me know when it comes up on the screen. Does it come up? Has the PPT come up on the screen? No, not yet. Just a moment. Result, if it's there. Okay. Get this. Okay. Now it should be. Okay. On enough. Now it's visible. Now it is visible. Okay, good. So yes, this was where we were. Last part. Original data and different subsets. What we are feeding from this. Other thing to do is that once you have these different subsets, what you simply do is from these different subsets, you get different models. You can already see that model 1 is there, model 2, 3, 4, 5. Combine the prediction for generally, I mean, whatever the methods that we have talked about, either a soft voting or a hard voting for the prediction part. Okay. Okay. Yeah. Use a soft voting or a hard voting, or again, if it's a regression case, use a simple average or a weighted average and get the combined prediction from this particular. Okay, so the good thing about this step application is that all the features, whatever features that you're using, have a equal selection probability. Equal selection probability, and very important is this homogeneous weak learners. All the learners which are there, they are homogeneous and they are being independent of each. One good thing about this step application process, and then by using homogeneous weak learners, is that data selection part and the model building part simultaneously. The only part when everything gets indicated is the combination part. Majority voting, whatever you are doing, that's the only part where it gets combined. If some models are taking longer than the other model to run, it will, the performance will suffer a little bit. But at the end of the day, will, since they are running all in parallel, is amenable to all parallel computing, all the newer cloud kind of systems which are there. They are all amenable. Right? Okay. Coming to the tagging beta estimated, right? Beta estimated, what that there is some kind of a base estimated model that you get. Typical the tagging method that we have talked about right now. This one can use both for both classifier as well as the regressor problem. First, random subset straight from it. And then here, unlike what we have talked earlier, all the features, not a subset of the features, but all the features. The only difference is that here data how it is created is by the swapping process. But again, subset of all the features. And the base estimator that we have specified. Now, when you are base estimator, what you take the base estimator from any of the trained or learned model. You can run a base estimator on the main model itself to a simple train test script, figure out the hyperparameters, all of whatever is required there, and then you pass that particular model to all this data subset. Look the prediction of the model, and then finally result from this. Right? Pretty simple. Nothing complicated. The only part is that the base estimator already pre-configured, and here all the features rather than using the indicative diagram for the same already shared with you. Might have already received it. So for a classification problem, the base learner, different base learners is what you're having. Gives different models that there because the subsets are different. Base learners are the same. At the end of the day, some test samples are there. Put the test samples in this ballot box. See how these models they are giving the result on the test sample from this ballot box. Major task for us. Important things. One is that base learner same, and these different samples which are there all present in different samples, right? Okay, go ahead. First example is the that of a bad shift. Its own data sample. Predictions are based on the agreed value. All the features are given. Base estimator the decision tree there. Maximum number of samples to specify, number of basis estimators or 3 to use, and number of features. Might have specified that I am going to 5 features. Features will not be there. 5 features. Change those number of features. Fine. Okay. Questions are there. Amritanshu is saying again voice is breaking. Again, is it happening for everyone? I'll just turn off the video probably. From my end, I have done everything which was there. But yeah, I've turned off the video. Is the video voice breaking for everyone? Once again, for everyone, or some of you breaking for everyone? Not very sure. Maybe I don't know. Maybe there is some network issue. Come in. I'm not very sure about that. But again, let's continue. Let's continue. Okay. That I have already talked about, right? How illustrating with our chef happens. What this chef has figured out that the chef is having several different cooks. 1, 2, while the one always creates a perfect dish, what the cook 2 generally gives more salt, and let's say less oil, less spice. For cook 3, it gives less salt but more oil, less spice. For cook 4, it gives less oil, less salt but more spice. Aggregate 1, cook 2, cook 3, and 4. Right? We have given them the same ingredients. It has been given the same ingredient. Performance of them are different. Then the ensemble model which you get. Otherwise, what you can also look into is giving the same cook. So cook A across 4 different kitchens. And this different kitchens, what it is having is a different kind of the ingredients. The C for kitchen 1, they are having ingredient 1, 2, and 3. For kitchen 2 is having ingredient 2, 3, and 5. Kitchen 3 is having ingredient 1, 2, and 4, like that. So the same cook, right, or the same model, when we work on the different ingredients which are there, it will give rise to different tasting foods. Finally, when you blend all of it together, it will probably give the good tasting food which you had all that. Right? Was what I wanted to illustrate the chef that we have. Okay. Right. Yeah. Tagging process once again. Multiple data set, classified, and combining the. Okay. Coming to the part of a random forest. Random forest once again is an ensemble technique. I think I've mentioned that even in the decision tree class. What happens in a random forest process is that you create different decision trees based on different samples of the data. Right? Now, what will happen is that because different samples of data has been exposed to the decision tree, it different kinds of altogether. This is tree 1. This is the other tree. This is the third. We have probably used the same learning algorithm, the same hyperfitting parameters, but because of the samples exposed to them are different, the trees which get generated are different. At the end of the day, the combined output, what they gives, that will only be the final result based on the method that we have spoken about. Out here, that is asking question, you features, not very sure what saying, right? I can give different samples with different features. See, if when I'm giving different samples of the data, see, so what will happen is based on the representation of the features samples to create these different trees. So I think you have seen that the tree in the middle, it gets level 2 in both these branches, but the tree on the left side gets to level 2 only on the left side branch. On the right side gets to level 2 on the left side branch only, but again with one, because different subsets of data were probably used. Now, random very wonderful means of finding out the feature selection. Sometimes this random forest is being used for feature selection. How? When you have exposed this random forest, different subsets of the data, different subset of the features, what you will do is at the end of the day, find out that how many different features have come in. Most of the trees which have been created, simply do a sorting of them in a descending order. And the feature which has come out for the maximum number of times, that is probably the most important feature with the decision tree, and like that. So the top few features you can probably take, and using these top few features which are there, build a decision tree, and then finally see what kind of a performance. That when you have data, hundreds of features, which is what happens in real life data set, a method like this, a random forest, give you a lot of time and help you find the variables which are important for your modeling. Now, once you get the important variables, you may no longer want to remain with a random forest. You can switch to a decision tree if you want some more explainability, or maybe move to some other models. But the very fact that you have been able a subset of the different features, you are not using all those 100 features which were there. Already you have the subset. That itself reduces the complexity of the model work very extensively. Okay. Yeah, just random forest. Let's so my question to the class, you see the data out here, how the model is being aggregated. Is it via a hard voting or a soft voting if we are using this particular method? Is it a hard voting or a soft voting? This particular tree is using the final result. Okay, so already Puna has given the answer, Anu has given the answer, yes. In this particular case, it's a soft voting. Why? Because we are not taking just the result from the trees, but we are also looking into the different probabilistic values coming from these different trees which are there and combining all of it. Right? Good. Very good. So yeah, pretty powerful. The model we have already talked about it. The maximum features, number of estimators, minimum number of sample trees which are there. So of this, you remember, for a decision tree, minimum sample leaf was already something that we have used. Other different thing which has come in here is the number of estimators. You are Find a random forest. You also need to specify the number of estimators which you need to create on this, and then also the maximum features that you need to try on the virtual. If you are varying the features also, right? Say you have given the maximum feature as 8, and if there is a minimum feature value m, so all the way from m to k, it create different partitions or subset of the data. Create random forest, right? Okay, let's go ahead. Okay, now that we have talked about bagging, let's come to boosting. See, a common question in interviews be the difference between this bagging and boosting. How bagging and boosting are different. How it is different is that, unlike other methods which we had, here first what you will do is on the entire data set are create your model. But then how it becomes an ensemble technique? Hold on. So what you are going to do is that once you have created the model on the entire data set, the first case of creating the model that you have had. Right? So this particular part was successfully classified. So give a tick to it. This data part was not properly classified. This data not probably perfectly classified. But this once again perfectly classified. The next iteration, what you do is when you are creating the data, ensure that you give more weightage to the ones which were incorrectly classified. So the probability of selecting the data points which were incorrectly classified, that you increase. The ones which were correctly classified, decrease that. Right? What we have done. And in the second run, what has happened is that this has been correctly identified. This has been correctly identified. This has been correctly identified. Unfortunately, this has been misclassified. Right? Earlier, this particular part was properly classified, but this particular run has been misclassified. In the next run, what you do is, once again, the ones which are correctly classified, increase its probability, right? And then the one which was incorrectly classified, increase its probability of selection. And then the next run, what we are seeing is that the first part incorrectly classified, this one correctly classified, correctly classified, correctly classified. As you understand, in the next run, what you do is the one which was incorrectly classified, is that now it's correctly classified. This one also correctly classified. This one also correctly classified, and this one adding more subsets of the misclassified data. Right? Then this particular combination, at an example of a state. At every subsequent model, the lacuna from the previous model has been tried to get addressed based on the subset of the data which was selected. Give more importance on the ones which were incorrectly classified, that we are getting more represented in the data, and via increase in the number of data subset, decrease in the number of data subset, iteratively do that, and finally get a model which probably has been a good classifier. My question in the class is, what can be a potential problem of this particular methodology. A potential problem of this particular methodology. Right? The method is there in front of you. What can be a potential problem with the methodology? Potential issue that you see happening in this particular case. Anyone? Anyone? Some potential issue that you see happening in this particular case. Yeah, anyone? Any potential issue that you see happening here? Okay, let me see. Yes. By doing this iteratively, chance that final model which will be created, it might have overfit the data. Thank you so much, Purna. Yes, that's a problem which might have happened, right? This model might suffer, methods sometimes might suffer from overfitting. That is a potential problem that we are going to have out. Good. Yeah, one thing which you have seen that one very important part is a sequential technique, right? Unlike the bagging sequential technique, it also leads us the part that in terms of the speed answer getting, the model is converging, will probably take a higher time compared to what we had for the bagging, right? And also tendency to overfit the. So here the bias generally will decrease over the period of time. But yeah, in the process, if overfit, and one of the reasons of overfitting that the weak learners, in most of the other cases, in the parallel process that we have talked about, many different weak learners were created. But here, in this particular case, because we are taking the entire data set, trying to fit the model, right? Running on the same model again and again. What is happening is that from the part of a weak learner, we are coming to the part where actually the strong learner is being boosted, or again for any boosted content methodology. Right? So yeah, is that in tagging was parallel, but in the case of boosting, as you see, that it's the sequential process. One thing is that time which will take for a boosting process much more, one, and the other part is that it might have a tendency to overfit the, right? Okay. One for this as ADA boost, right? ADA boost, what you are doing is original data there. All the points, they are having the same kind of weightages. All the points, they are having the same weightage. And once you have this classifier, as you can see in this classifier, this negatives, this is the decision boundary which has been created by the classifier. Draw the discrete boundary for you. Boundary with the classifier has. Now, as we can see, there are some points which are over this boundary, some points which are below this boundary. Points which are over this boundary, they are the negative points. Points below are the positive points. But what we are seeing is that this point, and this point has been correctly classified. So the next time what we did was these points, more instances of these points have got created, got the model. Time once again, when I'm fitting the tree, it's created a different tree this time. The tree has got created this time, right? Here, 3 points are there which has got misclassified, which are marked out here. This point, and this point. 3 points have got misclassified. So the next time, what will happen is the weightage of these 3 points again will increase. Vis-a-vis the other part, right? All the probability of the other parts of the data proportionally decrease, right? So all the other parts you've seen that proportionally they have decreased, and once again the model that is got, right. So finally, when you have combined all the classifiers that were created, the final decision boundary that you get. The final decision boundary that, and as you have seen out here, the final decision boundary classifies all the data points correctly. There is this chance that this final classifier created might have hit the. That's a potential challenge here, right? Steps are there, right? Whatever I have told about, those are the steps. It's written in words. You can use for your reference. Going to the slides, and use the advantages can be used for many different kinds of classifiers which are there. Definitely, it increases the classification accuracy. Why? Okay. Anyone can tell me that why it increases the classification accuracy? We've already seen the result, the example which I've showed you. Why do you think that can increase the classification accuracy? Or rather, I may rephrase the question: in which kind of a models this will give you superior results compared to base learners? Which kind of a problem this particular methodology can give better results compared to the others? Yeah, one. Nice balance. Okay, fine. Classic balance, biased model. Okay. Anyone else with some other answer? Balanced, biased model. Models having high variance. Okay. Okay. I'll tell you. Right? But variance, low bias. See, low variance, low bias is actually something that we aspire for in any models. That's what we look out for, right? Low bias and variance. Nothing specific to this. See, here you see how the models are getting created. Right? Just pay attention back to the model. The model. A very simple model has been created out here. Very simple model. See this particular part of the model. Very simple model. This model has been, right. That's why what is happening is that particular model, what you are seeing, it have a very high bias. Makes big assumption about this particular model. So if there is non-linearity, the decision boundary, all the 3 decision boundary that has been created are pretty linear. Linear decision boundaries have been created. So if there is non-linearity, the data, the decision boundary, by using simple, normal based learners can't attain that non-linearity. But once you have combined the different base learners. Combine the different models there. Clearly get the identify the non-linearity part, which clearly has been able to do that. Whereas the other case was not possible. Model on its own, however hard you might try, probably would have been never be able to get a polynomial kind of curve. If there is asking combine classified equivalent to decision tree with depth of 3, no, not really, not really. Combined classifier, what it is doing is that it's creating three different decision tree, or for the sake of the matter, any model it's creating, right? So, give an example. Let's say that the y and this is your x. The first model is that y is less than a particular value, let's say k1, then plus else minus. That's the first model which has been created. Look into the second model. In the second model, the tree or whatever model has been created is not on y but on x. Right? So here it's saying if x is less than some value k2, then negative, else positive. And see the third case. Once again, this third model has also been created on x. If x is less than some other model, some other value, then it is minus, else it is plus. Right? Now you combine this. Right? In fact, you can see that this little model actually a redundant model. If you just combine the first and the third, you're probably getting combined model, combined classifier. It doesn't have to do anything with decision tree of level 3. There have been decision tree of level 4, 5, whatsoever. There, right? But again, three different kind of properties have got from it. Right? Okay, very good. Let's move ahead. Up the okay. The advantages sometimes noisy data, outliers. Yeah, that is always a outliers is a big problem. Noisy data is a big problem. Why? Because see, since sequentially tree is getting generated, always try to create the perfect model from this noisy data, and in the end, it will result into an overfitted tree that you get. That's the problem. Find out here. Right? Okay. GBM, these variant boosting machines, these are XGBoost. These are some of the new methods which are out there in the market. This works, they are very recent pieces. Some of them are as new as 2017. So what this GBM model will try to do is that it will try to fit a tree on the residual error which is there. Try to fit a predictor on the error which is remaining. And continuously what it will try to do is it will try to ensure that this error it gets reduced to the maximum. Right? Not find the example in any of the books. Been able to curate an example for you just for your sake of understanding how it happens. How it happens, but an example. Yeah. The example. So here is some years of experience and the corresponding salary for those years of experience. Right? as you can see that this is not a very consistent data. For years 5, salary is 82,000 or something. 7, it is 80. For 12, it is 103. 23, it is 118. 25, all of us are at 120, 172. 28, sudden dip, 127, right? 34, 189, right? 35, 99. So again, you can see that it is not very consistent, this particular data, right? So finding out a linear model from this is going to be a challenge. Now let's look into GBM so that it can help us fit some model onto this data. First, let's look into the error which is there, right? First step is to look into some kind of a error. A function f0x, something that we use, and a simple mean squared error, or again a mean absolute error is something that we taken from the model. Show you the outputs here. See, my first model is nothing but a simple model, which is nothing but an average of all the data points. If you average this out, 134 is what you get. It's the average model. And this particular part, y minus f naught, simply the error coming out of this model. So this y minus f naught, if you understand properly, it is simply nothing but yi minus y bar. What we are looking at. Yi minus y bar. Sum of y is this particular column. Once again, now once we have this, the next thing what we'll try to do is we will create another model which will combine both the first y as well as this y minus f naught, whatever we have got, and this is what we get. Right? This particular part, the f1 model that we have. The new model that we have created, drop this. Just okay, forget that. See, what I've done is the parts of the tree which is there. See this part. One of the split we have made for the current tree for the case where x is less than equal to 23. Other cases where x was greater than 23. And for this particular part, average comes out as minus 38.25. Here the average comes out as 25.5. That is the output from a very simple model that I've created. A first level decision tree split we have done. Now we'll combine this with our model. How? So minus 38.5 is when it is less than 23. More than 23 is 25.5. What right now we have simply done is that whatever was the if not value which you have got earlier. So if not, if you remember, was the average model which you have got. With this, we are adding this H1 component, which gives rise to parameter which is F1. So F1 right now is having this values 95.75, 95.75, and then 159.5. Now, what we are going to do is we are once again going to find out error there. Earlier we had taken this y minus f naught, and this time we'll take this y minus f1. Now you see y minus f1 gives me this is values minus 13.75, 0.75, 7.25. These are the values that I'm getting from y minus f1. Once again, if I fit another tree on this, right? This time I'm fitting the tree on y minus f1, the error part. Then after the tree is being split, right? This part 6.75 is coming from the left side part of the split, and minus 27 is what you're getting from the right hand part of the split. Right. Once again, what you do is that to combine this to give you a new model. So how we are going to combine? Simple. F1 plus this H2 value, whatever you have got, it will give you the new value. So F1 plus H2 is giving you F. So 102.50, 102.50, 166.25. This is what you are getting as the new part. Y minus F2, once again, this is the error that you are getting. Right? And like that, once again, you get H3. What you try to do is iteratively this particular way to try to reduce the amount of error which is there. Already you can see that the amount of error which is there. So if you sum up H3 combined error which is there, if you sum that up, right, find that already the combined error is much lesser compared to what you had started off in the very beginning. So repeat this till the point where your error becomes very much minimized, and probably that is where you can stop. Right. So many weak learners you take into account and iteratively gets optimal model for you. What's the potential disadvantage of this particular method? Potential disadvantages. Potential disadvantages of BM. Potential disadvantage. Advantage part, so we have already discussed. Disadvantage, some potential disadvantage. Anyone? Potential disadvantage of this. One of the potential disadvantages of BM that takes a lot of time for the model to converge. Lot of time for the model to converge. So on the advantage part, right? I mean, the kind of results which GBM will give you. Very, very difficult to pick that kind of a risk. Right? Very, very, and even the loss function that we have spoken about. Right? So I've just taken a simple average and found out the deviation of the value from the actual value. There are different kinds of loss functions that you can optimize. Right? It doesn't stop you on that, but of the module is working in this particular fashion. Data pre-processing will also not be required. Right? Categorical, numerical, so anything to it. Work on. So the advantages, disadvantages, right? So once again, can cause overfit. See, most of the cases, these models which are being built sequentially, one of the common traits of models is that it tries to overfit the all the other things they do to try to overfit the data. And computationally very, very expensive. Not only expensive, it's very expensive. To run GPM in your system, in your laptop, find that it's a lot of time for the model to converge. Right? And then the other part is that one of the advantages that we had with decision trees was final model that you get was interpretable. Here the final model that you have got very difficult with the final model. Right? Because again, there will be multiple which will get repeated in this process. I'm sorry. That's one of the. So that is the problem for bit kind of search with the part. All heavily computation, and that's the reason why sometimes this model is not that much. Right? One of the disadvantage of this GBM was this particular part where it was slow. In XGBoost, what happens is that it tries a lot of parallel processing, right? But earlier with the random forest itself, it was creating multiple different forests. In the case of XGBoost, same methodology which is being used for GPM. It tries to replicate that entire process parallel. That way, sometimes it converges, the speed becomes higher. But once again, at the cost of the computation. GPM itself is very difficult to compute, as you have seen. And here we are running multiple GPM processes in parallel. So we are taking a bet or a chance that, okay, some of this will probably converge faster compared to the others, and you probably stop at that particular point. Right? So in that way, XGBoost probably gives you result faster, but again, at the expense of computational skill. Right? Other part in XGBoost which happens, that part of the values is there being handled separately, and all the nominal values which are there, categorical values, is converted to numeric values by a one hot input. So again, that particular part is where there is some little kind of a computation stability which comes in. So if there are many different nominal values, many different categorical values there, so this XGBoost will probably not work out. Handle that. Also something which is called light there, as you can understand that it is the lighter version of the GPM which is there, right? And considerably faster than XGBoost. The word light, right? This one also runs on distributed computing processing, and the distributed data, the global distributed data, the global parameters, it shares the local trees. That's how it achieves high speed. And then finally, a new model CATBoost, I think, just came in the market around in 2018, which is called categorical boosting algorithm. More amenable to handling categorical variables, which generally is a tedious process if there are a large number of such variables. One hot encoding, but exponentially increasing the number of features that you are taking model. CATBoost can automatically deal with categorical values and doesn't require extensive pre-processing learning algorithms. But some of the boosting algorithms which are there. Right? Last thing that we have to do today is this part of stacking. What happens in the stacking process is that multiple machine learning models are there, which are used to generate output from the model. And then what happens is top layer of the models, they help in the further junior models to take the further decision, right? So yeah, how concept diagram of stacking, different classifiers are there, output values are there, and that goes into a different classifier. What one thing to note is that output value, it gets into a different classifier. Now, how does this happen? Right? You have this training data which is there. Let me show you of this training data. So, the feature 1, feature 2, feature 3, and then this is the target. Right? So different features are coming in, and for the target, some value. There's a V1, V2, V1 like that. So what each of this after this training process, what happens is classifier is giving you some output value for the target, right? V1 or V2, whatever is there, V1, V2, whatever is there. This one also giving you some output V1, V2, whatever is there. This one also is giving you some output V1, V2. Is there. So the target values, the output values, what you do, that combine these output values all together. So these values right now, the V1 value coming from here, V1 coming from here, V2 coming from here, that itself becomes the feature for the subsequent model. And then there is another classifier which train on the output value of each of these classifiers. vis-a-vis the actual target. And then finally coming from this one, right? Anyone who did not understand this, please tell me, I'll explain this again. Anyone who did not understand this, please tell me, I'll explain it. Just that, yeah. So Dipti, I'll repeat. So first, what you do is that the data split into this 10 different parts. And this base model is fitted into this 9 parts and predictions are made for the 10th part. Right? What it generally do for any kind of a pain test split kind of thing, which is there. Now what we are going, whatever is coming as the output from this part, let me from each part of the training data sets. Let's say that we have fitted a decision, right? Output of the decision tree is kept as a new feature. Once again, I'm repeating. Feature, what might happen is that, let's say that we are trying to predict something like, churn, no churn kind of thing. So the output of this decision tree will be churn, churn, no churn, 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 no churn, like this. And I'll not stop with the decision tree. I'll probably also use another KNN model on this. Right? What this KNN model is going to do is, once again, it will have, say, let's say churn, no churn, 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 no churn, churn, like this. And maybe also some neural network model or something. So whatever I'm getting as things. So here I'm getting churn, 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 no churn. The features in model. And then I also have the output from the actual data here. Let's say the actual, this one is churn, 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 no churn, no churn, like this. So using this output of the feature of the different models, I'm trying to predict the output. So again, there's some question from is asking the baseline is homogeneous or heterogeneous. Most of the cases we take heterogeneous learners. Heterogeneous learners. Right? Okay. So model predictions based on the test data. So KNN, we have pain prediction test and the test prediction set. What we finally come across with part of the pain data set, and then what that is what it is being used. Not something that I endorse or again the machine learning endorse, but again, see what we are talking of here in ensemble model are nothing but different strategies which is there. And strategies there. So here the other strategy. Mainly, as I said, that heterogeneous learners are generally being. I have not seen cases where homogeneous learner you're using here. Heterogeneous learners being used because again your trained data and your validation data, they are already not able to create any subsets out of this point in homogeneous weak learners out here. You can use homogeneous weak learners, but yeah, then you probably have to have different this fine-tuning parameters for those. So yeah, like this, apply multiple base models on the data and from that, whatever output that you get, output value itself, you use the training for the what happens of a stacking, right? And then it's a possible to do a multi-level stacking out here. Multi-level stacking out here. Stacking, see, particular occams is the principle which I mentioned in the previous model class. Here, models, they are pretty simple compared to combined complicated models. That is the basic underlying parameter of this stacking process. But this whole part of using the model output from these models and that using as a feature prediction. In statisticians, they indeed have their doubts how effective, but again, never, as I said in the very beginning, that the case of machine learning accuracy, how accurate it is, that something which determines the performance of models, right? And the last one for the blending, right? The blending part is almost a similar approach to stacking. What you do out here is that make the prediction not on the training data set, but only on the validation and the test data. And these validation predictions, what we're getting, are used as features builder. Unlike previously, what's happening is that there's a training set on which training the data. There's a validation set on which you are getting output from the training model which you're getting. And this particular part is being yet make the final prediction on the test. Again, another variation of the stacking. There, people are indeed using this kind of models, but the disadvantage in all these cases are that are using the explainability of the model. How this model will perform, right? Taking a generalized view of this model, totally doubtful. But again, some of the cases, as I said, that because people are more concerned with accuracy and not how it is working, it's fine. For example, this is the smartphone which I'm having. I'm not really very much bothered as to how this fingerprint sensor is working. As long as the fingerprint sensor identify me and block out anyone else who's not me, I'm underlying what kind of a model is it? Blending, stacking, tagging, neural networks, deep learning. I'm not at all bothered. Okay? So again, the ensemble model, the entire ensemble piece, ensemble field, gets some kind of a eyebrow from the statisticians because the part will not be right. Okay, so I'll stop here. But again, right now I'm open taking questions from you part. Open to taking questions from your side. Right? Have any queries, doubts? Right? Be good time. Discuss that. Yeah, questions. If I can get some questions. Okay, so Pinkesh is asking the T question pattern. Yeah, so Pinkesh, as I have mentioned in the very beginning, for the TEE, whatever we have discussed in the class, whatever is there in the slides, will come from there itself. Won't have to look into some external materials for the TEE part. As long as you have watched through the videos in the AC part, as long as you have attended the classes, you have understood what has been shared with you, it's good enough for the TEE. Okay, he is asking if you will have Python questions. No, I have not put any Python questions in the TEE part. Right? The next module, which is the advanced machine learning part, that is where we'll probably have a lot of Python thing. But at least here in the TEE, there are no Python thing. It will all be theoretical questions or special kind of with there in there. Again, as I've said, will there be numericals? Yes. Now the question papers have indeed given numericals, right? Simple calculations which are there, right? As long as you have been able to follow what we have done. See, simple things like again, things like what will be the output of the this voting method, right? In a particular scenario, what will the output from regression in a simple averaging or weighted averaging, those kind of things. From decision trees, output of the entropy, index, reduction impurity. These are some of the things that are being asked, covered in the numerical part. Again, as I said, that as long as you have understood what we have done, it should not be a challenge for you. Not be a challenge, right? Yeah. Any other question that you are having? Any other question that you are having? Only one thing which I'll request all of you for the TE part, please write the point, right? I've seen in some earlier batches, what they have done is they directly go to the internet and get the answer and copy paste that answer in the browser. Whenever we have detected this kind of instances, right, there's a strict instruction from the university to give complete 0 marks, right? Though I'll not be evaluating your answer sheets, but still, some of the instructions is there. So I have the model answers which are there. As long as you are close to the model answers, there's no reason why you should not get full marks. In fact, many people, they have got full marks also in my papers. That is not something that you should be concerned about. Only thing which is concerning is that there are some experiences, some malpractice. The university takes that very seriously. So please avoid that. I've seen people, I mean, like copy pasting in there, this thing. And again, what we have done, what we have seen is that like things like the fonts, they are coming in a different pattern, different fashion, right? Very simple ways which can be caught. And then once you run this plagiarism check, it directly gives you the website from which the answers. Please don't let that in your grades, assuring you that exams not be very tough. Okay, Joginder is saying there is no internet allowed. Yeah, Joginder, that's what you think, but some of your seniors, they have found out innovative ways in which probably they can get this thing done, right? Ways in which not allowed, we all know, but yeah, that is the reality is far from. Okay, any other question that you're having? Any other question that you're having? Please write to the point. I'm clearly mentioning that there is no credit, extra credit. Write long answers. You can write in bullet points. Point, that is where the chance of scoring the maximum marks. How we evaluation based on points, that whether you have been sufficiently covered all the points which were necessary. Right? That's what we apply. As long as you have done that. Any other questions that you have? No? Okay. So in that particular case, I'll take your leave, right? LS4 is already shared. LS3, as we speak, right? Just after this, I'll just mail him and just check that why it was not shared. Okay? I'll do that. Please be assured. Not to worry. But again, I'll come back to you for this advanced machine learning. So yeah, if you have not received it, please make it a note. Mention that. Right? So I'll personally follow up with the university to see that. LS4, LS3, both I have shared. Not received it. I'll personally follow it up with the university. Not to. Fine. Okay. So let's break for today. So tomorrow, I think this batch only is coming for the advanced machine learning. Same batch. Okay. Again, tomorrow for the advanced machine learning part. Meanwhile, let me drop a reminder to the upgrade team again. The advanced machine learning, the first piece tomorrow we are going to do this clustering. If possible, just read particular is content which is there. This I have not shared with the upgrade team as of now. So tomorrow after the class, because there are some contents in the slides which I can't directly share. Let me first take up the class, and then tomorrow after the class, I'm going to share the LS1 for the advanced machine learning. Right? Thank you, everyone. Thanks for being there on a Saturday evening so long. Right? I'll see you again in the next class. Take care, all. Good night.